Right, this video is going to cover all of electricity and circuits, the entire unit. Now, this video is specifically for the Edexcel exam board, but it will be helpful for any exam board because all exam boards cover very similar material. This video will be useful for any course, double award or triple award, and it's for any tier of study, so foundation or higher. I'm going to try to get through the content as quick as I can so that this video will be great for some last minute revision the night before your exam. Right, what I've done is I've broke the syllabus down into all the different statements that the exam board says you've got to learn. And I'll just literally, methodically cover the whole syllabus one at a time. Now the electricity unit's quite a big unit, so this is probably going to be the longest video, so bear with it. Right, describe the structure of the atom linked to the position, mass and charge of protons, neutrons and electrons. Okay, so the atom, it's got a nucleus in the middle, which has got the protons in, which are positive, and the neutrons in there, which are neutral, zero charge, and then orbiting around the outside in the shells are the electrons. The first shell holds 2 electrons. The electrons have got a negative charge. The second shell holds 8 electrons. Right, so the position. So in the nucleus, you've got the protons and the neutrons. The mass. Well, the proton has got a relative mass of 1. The neutron got a relative mass of 1, and the electron has got a relative mass of 1 over 1840. So it's nearly 2,000 times lighter than a proton and a neutron. The charge, well, the charge on a proton is +1, charge on a neutron is 0, the charge on an electron is -1. And where do you find the electron? In the shells around the outside. Every time that you see one of these codes, this is a lesson code in yellow. So this tells you what lesson it came from in the Pearson textbook. Right, the second statement, you've got to be able to draw and use electric circuit diagrams representing them with the conventions of positive and negative terminals and the symbols that represent cells, including batteries, switches, voltmeters, ammeters, resistors, variable resistors, lamps, motors, diodes, thermistors, LDRs and LEDs. I've got a nice video that covers all this stuff. So a cell looks like that. The large side is the positive terminal and the small line is the negative terminal. As I tell my students, if you add something it gets bigger, and if you take something away it gets smaller. So you can remember the small side is the negative side and the big side is the positive side. The battery is very similar to a cell. Looks like that. The switch, Harry Potter's glasses. So that's a closed switch. An open switch just looks like someone's left the gate open. The voltmeter. Ammeter. The resistor is just a rectangle, otherwise known as a fixed resistor, because its resistance can't change. Right, a variable resistor, it's got an arrow going through that looks like an upside down V. V for variable. A lamp, a couple of different ways of drawing it, either like that or like an X-Man badge. A motor, it's just a circle with an M. Diode, right, D, I, O, right, there's your diode. It's like the first 3 letters, isn't it? D, I, O. That's easy to remember if you think about it like that. Thermistor, it's just a resistor with like a thermometer through it. It changes its resistance as the temperature changes. LDR, so it's a light dependent resistor. So it starts off just as a resistor. Because they go on top of lampposts, better put it in a protective bubble. And then here's the light shining down on it. It's a resistor that changes its resistance depending on how much light's on it. And an LED is the same as a diode, but it gives out light. D, I, O, and then it's given off light. So there's a couple of little bits of light coming off it. Light emitting diode. Statement 3. Describe the differences between series and parallel circuits. Right. So a series circuit has only one loop. A parallel circuit's got more than one loop. Now if I quickly draw just a basic series circuit, I'll pop an ammeter in and a little resistor, pop a couple of resistors in. And if I draw a parallel circuit, battery, ammeter, do another ammeter there with a resistor, another ammeter there. Right, well, in a series circuit, because there's only one loop, the current can't split up. So the current will be the same everywhere. I should have really put another ammeter in there as well. The current in a parallel circuit can be different in different parts, because as the current comes down to the junction, which is basically just where the circuit splits off, some of the current can come along this top branch and some of the current can come along the bottom branch. So what we see is that the current is shared in the different branches. Now the voltage in a series circuit gets shared. So just say you've got 6 volts from the battery. If these are identical resistors, then they'll get an identical amount of voltage. So if I was to pop a voltmeter across there and a voltmeter across there, in this case you'd get 3 volts on that resistor and 3 volts on that resistor. So it's the voltage that gets shared in a series circuit between the components. Now in this one, the voltage is actually the same in every branch, because each branch has its own direct connections to the battery. So if that was a 6 volt battery, you'd have 6 volts on this resistor and 6 volts on this resistor. And you often get asked, how come a 6 volt battery can give out 12 volts? Well, it will, but it'll go flatter in half the amount of time. It'll only last half the amount of time. So the voltage is the same in each branch. So if you'll notice, it's the opposite. The current is the same, that the voltage gets shared in a series circuit, but it's the current that gets shared and the voltage is the same in a parallel circuit. Same, shared, shared. Number 4. Recall that a voltmeter is connected in parallel with a component to measure the potential difference in volts across it. Right, well I've just showed you that one. So here's a quick circuit. If I want to measure the voltage of the battery, I need to go parallel across there. So the voltmeter gets connected in parallel. Those lines are parallel, like railway tracks. Voltmeters measure volts. Number 5. Explain that potential difference voltage is the energy transferred per unit charge passed, and hence that the volt is a joule per coulomb. So potential difference is just a posh word for voltage. And it says it's the energy transferred per unit charge. So the way I remember this is that EastEnders equals the Queen Vic. Now what they're just saying is if you rearrange that equation to get the voltage, so therefore voltage equals energy over charge. Voltage is measured in volts, energy is measured in joules, and charge is measured in coulombs. So all they're saying is that 1 volt is the same as 1 joule per 1 coulomb. Now you actually get a mark sometimes, just 1 mark, in an exam for knowing alternative units for a quantity. Number 6. Recall and use the equation energy transferred in joules equals the charge moved times by the potential difference. By the way, every time you see one of these codes in yellow, that tells you the lesson that it came from, according to the Pearson textbook. Right, well I've just showed you this equation, so the only difference here will be they'll probably give you some numbers. So they'll just say there's a 10 coulombs of charge and the voltage is 5 volts, and they'll just ask you to work out how much energy there was in joules. If you want to see more examples of specific questions, then check out my videos where I go over past papers. It's in my past paper playlist. Number 7. Recall that an ammeter, which looks like that, is connected in series with a component to measure the current in amps in the component. So if you're going to measure the current, the ammeter actually needs to be part of the main circuit. So just say you want to measure the current of that bulb, the ammeter needs to be in the wire so it gets the same amount of current going through it as what the bulb does. Now on my video to do with ammeters, you'll realise that because the ammeter is in series in the main part of the circuit, the resistance of the ammeter has to be very small so that it doesn't affect how much current is in the circuit. It's no good adding an ammeter to measure the current if by adding the ammeter it actually changes the current. If the ammeter had resistance, it would change the current you're trying to measure. Number 8. Explain that an electric current is the rate of flow of charge and the current in metals is a flow of electrons. So there's an equation. Q is for charge, I is for current, and when you're talking about the rate, that's time. So I always think to charge your mobile phone, you need to put a current into your phone for a certain amount of time. Now all they've done is they've rearranged it so that the current is how much charge you've got per time, so per second, which is what we call the rate. Anything that happens per second is the rate. And in a metal, the current is always a flow of charge, and inside a metal it's electrons that's flowing. So if that was your wire, you've got all these little electrons that are flowing down through the wire. Now each little electron's got a little charge, so if you've got more electrons flowing per second, you'll obviously have a bigger charge, which means you'll have a bigger current per second. Number 9. Recall and use the equation charge equals current times by time. So that's what I've just talked about. So how much charge your mobile phone gets depends on how much current is flowing for how much time. So if you've got a current of 5 amps, let's say, and you leave it in for 30 minutes. Now remember, time has to be in seconds, so 30 minutes times by 60 seconds per minute. And that's your standard question. So that would be 9,000 coulombs of charge. Number 10. Describe that when a closed circuit includes a source of potential difference, there will be a current in the circuit. So basically, if you've got a circuit and there's no battery in it, you're not going to have any current. So you need to have a source of potential difference. So that could be a cell, or it could be a battery, or it could be a power pack. Now remember, a power pack is AC. which is current that goes up and down. So you could have that. The cell would just be like that. You can see I had originally drawn my bulb like an X, but you can draw it like this as well. Or if you have the battery, it will be like that. And you'll have a current flowing around the circuit. Remember, it's the same size current everywhere because I've drawn a series circuit. And I've drew conventional current as well, which comes out of the positive and goes to the negative. Number 11. Recall that current is conserved at a junction in a circuit. So this is Kirchoffs Law. What goes in must come out. Instead of current, sometimes they talk about the charge. The charge into a junction equals the charge out of the junction. In terms of a picture, there's the junction there. You'd have current 1, I1 going into the junction. You'd have current 2 coming out, and current 3 also coming out. So Kirchoffs law would be I1 equals I2 plus I3. In a proper circuit, it could be like this. So it would be a parallel circuit. Because remember, there are no junctions in a series circuit. So this would be I1 coming down there, I2 coming across here, and I3 going across there. And then obviously at this junction here, I2 and I3 are joining back together to make I1 once again. So this current here, if I had an ammeter there, that would also be I1. The current after it's joined back together would have been the same size as the current before it split up. Now just be careful, because sometimes they can say the current is going the other way. So you could have I1 coming in, and I2 coming in, and I3 leaving. So in this case, we'd have the amount of current that was leaving would equal the amount of current that went in to the junction. So they could say that that's 3 amps going in, and that's 5 amps coming out. And they'll say, what was this one? Well, if 3's going in and 5's come out, this must have been 2 coming in as well. So 2 amps coming into the junction, 3 amps coming into the junction equals the 5 amps that's left the junction. And you could have 8 amps going into this junction, and 3 amps coming out, and they'll just say how big is I3. So that would be a case of 8 amps, I2 is 3 amps. So what have you got to add to 3 amps to make 8 amps? I3 must have been 5 amps. That's a standard question. Number 12. Explain how changing the resistance in a circuit changes the current, and how this can be achieved using a variable resistor. So the symbol for a fixed resistor just looks like that. So if we've got 6 volts going in, and we've got a bulb and a fixed resistor, if this fixed resistor is 10 ohms, and then we've got this circuit here with a 20 ohm resistor, because this circuit has got less resistance, it'll have a higher current. Now I like to think of resistors as being like brick walls. If you had a river flowing, the higher that you build the dam, the water current gets less. So a bigger dam equals smaller current. Well, that's exactly the same as an electric current. If you have a small dam, so a small resistor, you'll end up with a large current, and if you have a larger resistor, you'll end up with a smaller current. So we use resistors to control the size of the current. Now if we were to use a variable resistor, we wouldn't have to keep on changing the resistors. So that's the beauty of a variable resistor. You just simply turn the knob and it affects the current in the circuit So you can produce all sorts of currents and all sorts of voltages on the particular component that you've got in series with the variable resistor. Number 13. Recall and use the equation potential difference equals current times by resistance. So this is Ohm's law. It's very common. And they'll give you a current and a resistance, and you can work out the voltage. And sometimes you've got to rearrange it. So something times by something, pop that into the bottom here. And then I've got voltage and one space, so that voltage must go in that space. And then just cover up what you're looking for, and what you're left with is how to work it out. If you don't know how to rearrange equations, have a look at my video called Magic Triangle. So if I'm looking for R, cover up R, so R equals V over I. And if I'm looking for I, cover up I equals V divided by R. Now often, there can be a couple of voltages. So if we say that this voltage here is 6 volts, and this voltage here is 2 volts, and this voltage here is 4 volts, and if it says that the current is 2 amps, if you wanted to get the resistance of the bulb, make sure you're using the voltage on the bulb, not the voltage of the entire supply. And if we had to get the resistance of the resistor, remember it's going to be 2 amps through both of these components because it's a series circuit. Now it's important to understand, because the resistance of the fixed resistor is twice as big, it gets twice as much voltage compared to the bulb. And again, if you ever want any extra help, have a look up here. Tells you what lesson it's from, SP10D. Have a look in my playlist, the Edexcel playlist for the unit SP10. I've got a lot of videos on my channel now, so most of these concepts are covered in greater detail. Number 14. Explain why, if 2 resistors are in series, the net resistance is increased, whereas with 2 resistors in parallel, the net resistance is decreased. Okay, so if you think about a resistor has got lots of little atoms in, and what it is that the current finds it very difficult to push its way through all those little atoms. It's what we call a lattice. So as the electrons are travelling through the resistor, you get a certain amount of collisions here, which slows the current down, and then you also get collisions here, which slows it down. Now just remember though, the current doesn't start big here and get small there. Because these resistors are in the circuit, the current is smaller anyway, everywhere. So the more resistors that you put in the circuit, the more collisions there'll be between the electrons going through the circuit and the lattice in the resistors. The equation we've got is that the total resistance equals the resistor 1 plus resistor 2. So if that's 10 ohms and that's 5 ohms, that'll be the same as a 15 ohm resistor. If I was to put another resistor in here that was 2 ohms, that would give us a total of 17. And that third resistor would be called R3. Now, if you've got resistors in parallel, instead of having just one route where the current can flow, we've now got 2 routes, which effectively means that twice as much current can flow. Now, the resistance will equal the voltage over the current. Because it's in parallel, remember, if that's 6 volts on the battery, you'll have 6 volts on that resistor and 6 volts on that resistor. So the voltage is going to be the same in each branch. However, the more resistors you've got, the more branches you've got, which means the current gets bigger. Now, if that current gets bigger, mathematically, the resistance gets smaller. So that's the way of thinking about it mathematically, which is probably a good way of thinking about it. Now, if you've got 2 resistors in parallel, the total resistance will be smaller than the smallest resistor. So just say that's 10 ohms and just say that's 7 ohms. All you need to know at GCSE level is that the total resistance will be less than 7 ohms in this case. If the smallest resistor was 5 ohms, then the total resistance will be less than 5 ohms. Number 15. Calculate the currents, potential differences and resistances in series circuits. So like I said before, if we start off with a series circuit, we put a volt, I call that voltage 1, call this voltage 2, and I'll call this voltage 3. Now the current is just going to be the same everywhere because it's a series circuit. And then we've got Ohm's law is V equals I times by R. So if we rearrange that, you've got I equals V over R, and you've got R equals V over I. So let's just say that V1 was 6 volts. If V2 is 4 volts, well, we know that V1 is going to equal V2 plus V3. So the voltage that you put in gets shared amongst the two components. So you've got 6 volts going in, and that's 4 volts. So V3 is obviously just 2 volts. So what we know is because there's twice as much voltage on this component, it must have twice the resistance compared to that one. Now if we knew the resistance of this, so let's just say it's 10 ohms, now we can work out the current. So I equals V over R. So take the voltage of that particular component, which is 4 volts, divided by the resistance, which is 10 ohms. So that means that the current is 0.4 amps, and that's 0.4 everywhere. So now we can work out the resistance of this here. So R equals V over I, which will be 2 volts over 0.4 amps. That'll come out as 5 ohms. So as I said, this resistance here is half as much as that resistance there, because it's only got half the amount of voltage. Just think about it being like an obstacle course. If this is a brick wall you've got to climb over, because this brick wall here is twice as big as this brick wall here, it's going to take twice as much energy or twice as much voltage to get over compared to this one. 16. Explain the design and construction of series circuits for testing and measuring. Right, a typical 6-mark question is it'll say, how would you design a circuit in order to find out the resistance of a bulb? I always like to base my explanation on the calculation. Now in order to get the resistance of something, you're going to need the voltage over the current. So tell the examiner we'll need a voltmeter to measure the voltage. We'll use an ammeter to measure the current. And we need some way of varying the voltage across the component. And we do that by using a variable resistor. So that is your standard circuit for testing and measuring a piece of kit. Now what you'll do after that then is they'll very often ask you to do a current voltage graph. So what you tell the examiner is start off with this resistor small and make this resistor get bigger and bigger and bigger, and as you do, keep taking measurements of your voltage and your current across the bulb, and you'll end up getting enough results to create a graph. That should be going through 0, 0. Now because the resistance equals the voltage over the current, you can see the voltage is getting bigger and bigger, and so is the current at first, but then the current stops getting quite as big. So because the slope is getting flatter and flatter, the resistance is getting bigger and bigger. '17 core practical. Construct electrical circuits to investigate the relationship between the potential difference, so that's the voltage, the current and the resistance for a resistor and for a filament lamp. Well, I've just showed you it for a filament lamp, so it will be exactly the same for the resistor, except obviously you'd have a resistor instead of a bulb. Now this time, the IV graph will be a straight line for a fixed resistor, because a fixed resistor should obey Ohm's law. So R equals V over I, where R would be a constant or fixed. Part B. Test series and parallel circuits using resistors and filament lamps. So to test a parallel circuit, what you'll be looking for is to just measure the voltage in each branch to show that the voltage in each branch is the same. So if I call that V1, V2 and V3, you'd have V1 equals V2, which equals V3, and it doesn't matter if that's a filament lamp or a resistor in each branch. And you could also measure the currents. So if I call that A1, A2 coming across here, and A3 coming across there. Then from Kirchoffs Law, you'd have I1 equals I2 plus I3. They're the standard parallel and series circuits. Number 18. Explain how current varies with potential difference for the following devices, and how this relates to resistance. So they're looking for the standard IV graphs for a filament lamp, diode and a fixed resistor. So a filament lamp looks like that. Now it's otherwise known as a bulb, and I like to call it a spulb because the shape looks like an S. Mind that's only when you've got the positive currents and the negative currents, and the positive voltages and the negative voltages. Sometimes it just shows you the positive current and the positive voltage without showing this back section, in which case it's just looks like a curve like that. A diode, well, a diode, D-I-O, I like to think of this part on the front as being a blocker. So if the current tries to reverse backwards, that's not going to happen. The current can only travel in the forwards direction. So it doesn't matter how big the voltage gets in the negative direction, your current will be nothing. And then in the forward direction, you've got to get the voltage up to about 0.6 volts, and then you start getting a current in the forward direction. So in the same way that each person has got their own unique fingerprint, each component has got its own unique current voltage graph. So a fixed resistor, that would look like that. So it's exactly the same in the backwards direction as it is in the forwards direction. And the resistance is V over I, and that would be a constant. So it's a constant slope everywhere, because the resistance is constant. For something like the bulb, the slope starts off steep and then gets flatter and flatter. So that means that the resistance starts off small and gets bigger and bigger. Now just think that a bulb gets hot. The more current you put in, the bulb gets hot, so there's more collisions between the electrons trying to go down through the bulb and the lattice of atoms or ions that make up the metal filament in the bulb. So you end up getting an increased collisions, which is basically resistance. Number 19. Describe how the resistance of a light-dependent resistor varies with light intensity. So what that means, put the resistance up the side, put the light intensity along the bottom. That just basically means when it's dark and when it's bright. So when it's dark, the resistance is high, And as it gets brighter, the resistance gets lower. But it's an exponential relationship where it comes down at a curve like that. And remember, an LDR starts off just as an ordinary resistor. Pour it in a little bubble because it could be on top of a lamppost and it might rain, so that protects it. And here's the light shining down on it. Number 20. Describe how the resistance of a thermistor varies with change of temperature, and it's negative temperature coefficient thermistors only. Now, a negative coefficient basically means as one thing gets bigger, the other thing gets smaller. So in this case, if the temperature goes up, the resistance goes down. It's what you call an NTC. You can get a PTC as well, which is a positive temperature coefficient, but at GCSE Physics we're not interested in that. Now it's exactly the same shape as what you've just saw for the LDR. Resistance up the side. This time we're putting temperature along the bottom, and then it's either cold or it's hot. When it's cold, the resistance is high, and as the temperature increases, the resistance decreases. And again, it's this idea of an exponential shape where it drops down quick and then it doesn't drop down as quick after a while. And a thermistor just starts off as being a normal resistor, and then it's got like a thermometer sort of shape going through it. 21. Explain how the design and use of circuits can be used to explore the variation of resistance in the following devices: filament lamps, diodes, thermistors, LDRs. So the circuit's always the same. I've already talked about that previously, so if I quickly draw that out. And you basically just change this for whatever component you want. You can see I've drawn a diode in this time. The circuit for the filament lamp and the diode will be exactly the same. The circuit for the thermistor, you'd need some way of changing the temperature. So let us draw that one for you. You'd have to use a water bath with a thermometer in, and just let the water cool, and you can measure the resistance. You wouldn't necessarily need a variable resistor. You could just put a fixed resistor in instead. Use some boiling water, and as the temperature drops, you'll be able to measure the current and the voltage, calculate your resistance using R equals V over I. And what you'd find is that the resistance would be low at first, and then it would get higher as the temperature drops. For an LDR, you'd use the same circuit, but instead of a water bath, you'd have a lamp. Make sure that the lamp would be at a fixed distance. That's a control variable. And you turn the power of the lamp down to decrease the light intensity. Or, if you've only got a lamp with a fixed power, move the lamp away. And the further away it is, that would be light intensity decreasing. So that's the distance in meters. Right, I'm going to cover statements 22 up to 25 all in one little slide because they all tie in together. Right, 22. Recall that when there is an electric current in a resistor, there is an energy transfer which heats the resistor. Right, you've got to understand the nature of resistance. If you've got a wire, that wire is made of lots of little ions, metal ions. You'd call them an atom, except each little atom has lost an electron. These are the free electrons that flow through the wire. Now, as those little electrons try to flow down through the wire, they collide into the ions. It's what we call a lattice of ions. Now, every time that the little electron bumps into the ion, the kinetic energy from the electron gets transferred to the ion. Now, the ion starts to vibrate more, And basically, the more something vibrates, the hotter it is. So basically, the wire gets hot. So the electrical energy is turned into kinetic energy, and that gets turned into heat energy. Now, statement 23 says, explain that electrical energy is dissipated as thermal energy in the surroundings when an electrical current does work against electrical resistance. So what it basically means is, as the electron is going down through the wire, it's doing work to push against these ions, which causes the wire to heat up, as I've just explained in 22. And that wire doesn't stay hot forever. The heat from the wire gets dissipated out into the surroundings. Statement 24 says, explain the energy transfer in 22 as the result of collisions between electrons and the ions in the lattice. Well, I've already explained that. The way I like to think about it is, every time one of these little free electrons bumps into an ion, it causes a tiny little bit of friction. And you know what happens when you've got friction? It causes heat. So it's the collisions that causes friction that creates heat. And finally, 25, explain ways of reducing unwanted energy transfer through low resistance wires. Well, if you can make the wire thicker, it gives the electrons more room to move, if you like, and so there's not quite as many collisions, and so that means that there is less resistance, and so less electrical energy is wasted as heat energy. So less electrical energy gets transferred into thermal energy. Remember, thermal energy is just a posh word for heat energy. 26. Describe the advantages and disadvantages of the heating effect of an electric current. Right, well, the advantages are for any devices that's designed to get hot. So if you've got a kettle or a heater, then obviously you want the electrical energy to turn into heat energy. Now obviously it's a disadvantage for anything that you don't want to get hot. So you don't want computers to get hot, you don't want TVs to get hot, you don't want radios to get hot, because what's happening is it's wasting the electrical energy because it's turning into heat energy. And that's just a few examples. Number 27. Use the equation energy transferred equals current times by potential difference times by time. E equals I times by V times by T. The way I like to see it is Emmerdale is on I, T, V. If you're in England, ITV is your independent television, Channel 3. And all that you'll get in an exam is they might ask you to rearrange it. So make sure you know how to rearrange it. Use your magic triangle, create a top shelf. Now a triangle's normally only got 3 things in, but this has got 4 things. Well, that's all right. Instead of just doing 1 multiplied sign on the bottom, you do 2 instead. And now I've got something times by something times by something, and I've got room for something times by something times by something. So shove that in there, ITV. 1 space, 1 thing, shove the thing in the space. And then you just cover up what you're looking for. So if you're looking for I, cover up I. And what you're left with shows you how to work it out. E divided by T times by V. If you're looking for time, cover up time. And that leaves E divided by I times by V. Then work out V. That would equal E divided by I times by T. And they'll basically just give you numbers that you've got to bang into the equation. Make sure your time is in seconds. 28. Describe power as the energy transferred per second, and to recall that it's measured in watts or watt. So power equals energy divided by time. If you're very powerful, it means you can transfer a large amount of energy in a short amount of time, which means lots of joules per second. And 1 joule per second equals 1 watt. Power is always measured in watts. If you've got a 50-watt speaker, it means it transfers 50 joules of electrical energy per second into sound energy. If you've got a 100-watt speaker, that means it's going to transfer 100 joules of energy every second. So basically it's twice as powerful as 50 watts. Think about a light bulb as well. A 100-watt light bulb is twice as bright as a 50-watt light bulb. That's because it converts twice as much energy per second. 29. Well, I've just explained this. Recall and use the equation power equals energy transferred divided by time taken. So I don't need to explain that any further. The only thing I could do is rearrange it. So magic triangle, do a top shelf, split the bottom bit up by doing a times by sign. I've got P equals E divided by something. So in this case, I haven't got something times by something, so I don't know what goes on the bottom yet. But there is something on what I call the top shelf. I like to write it like that. P equals E over T. So if E's on the top shelf out here, it goes on the top shelf in here. And now I've got two things and two spaces. Shove the things in the spaces. Sometimes the students say, sir, is it P times by T or T times by P? And I say it doesn't matter, because 4 times by 2 is the same as 2 times by 4. It will both equals 8, so it doesn't matter which way around you do the P's and the T's. And then cover up what you're looking for. So if you're looking for energy, cover up energy, and what you're left with is P times by T. And if you're looking for T, cover up T, and what you're left with is E divided by P. It's just a case of banging the numbers in. And again, make sure that your time is in seconds. They'll sometimes say there's a certain amount of energy and it's in 2 minutes. So remember to convert minutes into seconds. There's obviously 60 seconds in a minute. Statement 30. Explain how the power transfer in any circuit device is related to the potential difference, which is just the voltage across it, and the current in it. So that's just the equation P equals IV. PIV, power, equals current times by voltage. And we can see that equation again in statement 31. So it's just a couple of equations that we're supposed to be able to use. So if we go P equals I times by V, you should know how to rearrange these equations by now. So that would just be I times by V on the bottom. P would go on the top, cover up what you're looking for. So I would equal P over V. V would equal P over I. They'll just give you the numbers and bang them in. And here's another little equation here. Another way you can work out the power is if they give you the current and the resistance. And it's just P equals I squared times by R. To rearrange that again, it's just the usual stuff. Do a top shelf. You've got I squared times by R, and you've got room for something times by something, and then one thing left and shove it up there. So it's just exactly the same thing there. So I squared would equal P over R, and R would equal P over I squared. Just make sure you know what the squared button is on your calculator. Don't do the square root by accident. 32. Describe how, in different domestic devices, energy is transferred from batteries and the AC mains to the energy of motors and heating devices. So when they're saying batteries and AC mains, they just mean you're starting with electrical energy. When you're talking about transfers, you just do a little arrow going from one form into another. So when it's going into a motor, it's turning into kinetic energy. And if it's a heating device, it would be electrical energy. turning into heat. For a transfer, wasted energy comes down, so I guess a motor does get hot. So this would be wasted energy down there, and that would be useful energy across the top. If it was a battery, I suppose technically it would start with chemical energy, and that would get turned into electrical energy, and then it would get turned into kinetic energy and heat. 33. Explain the difference between direct and alternating voltage. So direct voltage, that is batteries and cells. Alternating voltage, that's the mains. Batteries and cells are usually about 6 volts. The mains in England is 230 volts. Now with a battery, you've always got a positive side and a negative side. But with alternating current, one split second that would be positive and then that would be negative. And then in the next split second, that would be negative and that would be positive. Now in England, that change happens 50 times a second. Now, however many times something happens per second, that's what we'll call the frequency. So in England, the frequency of the mains is 50 Hertz. 50 Hz. Now with the battery, the direct voltage, it just constantly stays positive and negative. So what that means is the little charges, the little electrons, they are always flowing in the same direction. Now I've done conventional current there, which goes from positive to negative. If we consider this circuit, what would happen is for a split second the electrons are flowing that way, and then another split second later they're flowing backwards again. So forwards, backwards, forwards, backwards. Now those charges flowing are what we call direct current and alternating current. Now with the chicken and the egg, we're not sure what came first, but with current and voltage we do. It's the voltage that causes the current. So direct voltage creates direct current, which is what we call DC, and alternating voltage creates alternating current, which is what we call AC. And if you were to look at that on a cathode ray oscilloscope, which is basically a screen that can show the voltage would be steady for direct voltage. For alternating voltage will go up and down like that. 34. Describe direct current DC as movement of charge in one direction only, and recall that cells and batteries supply direct current. Well, that's what I've just said. So direct current, the charges flow from the positive side of the battery to the negative side, and that is conventional current. Just say that the electrons or the charge moves in one direction. 35. Describe that in alternating current, the movement of charge changes direction. Well, that's what I said before. So for a 50th of a second, the current would be flowing this way, anti-clockwise, and then a 50th of a second later, the current would reverse and it would flow anti-clockwise. So remember, the charges that are flowing inside wires are little free electrons. So these poor little things don't know if they're coming or going. Because the flow keeps alternating, that's what creates alternating magnetic field as well, which is what we use in transformers. 36. Recall that in the UK the domestic supply is AC at a frequency of 50 Hertz and at a voltage of about 230 volts. Right, well, I've already said that a couple of times already, so I'm not repeating myself. I've already explained it. 37. Explain the difference in function between the live and the neutral mains input wires. Right, well, basically the live wire takes the current into the appliance, and the neutral wire completes the circuit and takes the current out of the appliance. So if this is your TV, this would be the live wire taking the current in. This would be the neutral wire taking the current back out, which completes the circuit. The live wire is brown and the neutral wire is usually blue. 38. Explain the function of an earth wire and of fuses and circuit breakers in ensuring safety. Now, I'm not going to go into too much detail. I do have a nice video all to do with earth wires, fuses and circuit breakers that you can check out in my SP10 playlist. The earth wire basically is for safety. It stops the appliance casing becoming live. That's for appliances with a metal casing. So it prevents you from getting electric shock. And fuses and circuit breakers, they are connected to the live wire, which obviously brings the current into the appliance. So if there's a current surge, first of all, the current has to go through the fuse or the circuit breaker. And if there's too much current, the fuse will melt or the circuit breaker will trip, which will break the circuit and protect the appliance. The circuit breaker does exactly the same, except instead of this line here, the fuse heats up, the circuit breaker would trip, breaking the circuit, protecting the appliance by turning it off. An advantage of a circuit breaker is that it works at a more precise current, so it breaks the circuit quicker than what a fuse does. Plus, a circuit breaker can easily be reset, but once a fuse is melted, it needs to be replaced. 39. Explain why switches and fuses should be connected in the live wire of a domestic circuit. Well, remember, the live wire is what takes the current in. So if you've got a little switch, that'll turn the current off before it gets to your TV. And also, if you've got a fuse, if it's in the live wire, that means before the current gets to the TV, if the current's too big, then the fuse will blow before the telly does. A fuse is about 10 pence to replace, a telly's a lot more than that. So that's why you place the fuse and the switch in the live wire, not the neutral wire. It would have already done the damage by then, wouldn't it? 40. Recall the potential differences between the live, neutral and earth mains wires. Right, well, the voltage in the live wire alternates between plus 230 and minus 230. The voltage in a neutral wire is nothing. That's why they call it the neutral. The voltage in the earth wire is also 0. So if you're comparing the live wire, which is 230 volts, and you're comparing it with the earth, which is 0, the difference is 230. If you're comparing the live with the neutral, the difference once again is 230 volts. And if you're comparing the earth with the neutral, the difference is nothing. It's a long time since I've seen that question asked, but it's still on the spec, so it could come up. 41. Explain the dangers of providing any connection between the live wire and the earth. Right, well, as I've said, the live wire is 230 volts, the earth is 0 volts. Now, what's going to happen is loads of electrons are going to go from the live to the earth, and that can cause an electric shock. Remember, a potential difference is what drives electrons. So there'll be loads of electrons over here that move across to this way to try to even out the voltage, and it's when that current flows that's when you'll get your electric shock, which could burn you or kill you. And finally, 42, the last thing that you need to know about electricity. Describe with examples the relationship between the power ratings for domestic electrical appliances and the changes in stored energy when they are in use. Well, remember, the power rating tells you how much energy per second something uses. Power equals energy transferred over time. So the greater the power, the more energy it uses per second. So changes in stored energy. Just a few examples. If you've got a bulb, that changes electrical energy into light energy. A hairdryer, that changes electrical energy into kinetic energy and heat. They are both useful types of energy. You could say that the wasted energy is sound. You get a lot of sound energy out of a hairdryer. And my wife's using the hairdryer first thing in the morning, I know about that. Wakes us up. And there's a couple of examples that'll do you. Right, if you like this type of video where I cover an entire unit, comment below and tell us what you think. If there's any improvements that I could do, tell us what you think about that as well. Now this is probably the biggest unit, so if I do videos like this again, they should be quicker. Am I going into enough detail? Am I going into too much detail? Just comment below. And apart from that, subscribe to the channel. It helps us out. Hit the like button. Share it with your mates so they can pass their exams as well. Work hard. Be nice. And I'll see you in the next video. Bye for now.